Evet, başlayabilirsin.
Herkese merhaba. Bugün Emir Demirel bize bir sunum yapıyor olacak doktora çalışmasıyla ilgili. Bu sunumun uluslararası araştırmacılara, öğrencilere erişmesini istediğimiz için bu noktadan sonra İngilizceye geçiş yapıyor olacağım. Soruları ama Türkçe alabiliriz ve soru cevap kısmında da Türkçe iletişim kurabiliriz. So let me switch to English now. So I'm very happy to welcome Emir Demirel for giving us a talk on his PhD research. Emir is an undergraduate of Middle East Technical University Electrical Engineering Department. Then he did his master's in Universitat Pompeu Fabra in Music Technology Group. I was the supervisor of his master's thesis. And it was a great pleasure working with him in the same lab for 1 year. Then he started his PhD in computer science department in Queen Mary, University of London. And his research in an EU-funded project, Music Information Processing Frontiers project. It's a big project that involves many PhD students, also involves companies. Emir also carried this research in collaboration with the company. I guess he will give us some information about that. Emir is an active musician. He is a very good bass player, a jazz player, but he told me that he switched to guitar, and I did the inverse. I was a guitar player. I switched to bass recently. The title of his talk is Automatic Speech Recognition from Singing Voice. The floor is yours, Emir. Thanks a lot for giving us this talk.
Thanks, Barish. It's a great pleasure to be able to give this talk today within the AIDA seminar series. And yeah, I hope one day after the pandemic we can play my guitar and your bass together.
That would be great.
I know we can play through Zoom or something, but there's always the synchronization problem, isn't it? I mean, you can't be faster than the speed of light. So there's always going to be. So I hope one day we'll play that. Hi everyone. Barish introduced me briefly. I'll switch to my presentations right away, and we'll proceed from there. All right. So can you see this picture? Is it clear? Well, I think it's clear. Anyways, yeah. Well, I wish that this was an interactive talk, so I could ask some questions and get some answers fast. But given the pandemic, it's not going to be this way. It's going to be a monologue, but I hope you guys enjoy it. Think about what you're seeing in this photo. Like, what's the first thing that you see in this image? Well, it's rather an easy question. Obviously, it's some lovely Italian pasta in a nice glass jar. But that's not the main topic of this talk. I'd like you to focus on that weird object on the hand side of this Italian pasta that has an odd shape that looks like a cone. Sliced off in the middle by a sword or a katana, something like that. Well, if you haven't seen one of those things or devices before, you're going to be hearing about it quite often in the last century also. These are called voice assistants. Some of you may have heard about it from Amazon's Alexa or Apple Siri. So in today's talk, I will be talking about one of the core technologies within these voice assistant devices. This technology is called speech recognition. And particularly, I'll be focusing on its application in singing voice. So yeah, I'd like you to remember this cute little image here that represents our speech recognizer that you'll be seeing quite frequently in this talk. I'm Emir Demirel. I'm doing my PhD in Queen Mary University of London as a part of the European-funded project, Music Information Processing Frontiers. And I'm supervised by Professor Simon Dixon, who is one of the most prominent and impactful researchers within music information retrieval research. And I'm also supervised by Professor Sven Albeck from Royal College of Music in Stockholm. And he's also the CEO of Doremir Music Research AB, which is our industrial partner in this project. So before I talk about speech recognition, I'd like to talk a little bit about my project. So MIP Frontiers is a PhD training network for 15 early stage researchers all around the world. And there are 40 universities involved in this project around Europe. Queen Mary from London, Pompeu Fabra from Barcelona, Telecom Paris Tech from France, and Johannes Kepler University from Linz, Austria. And there are a number of important industrial partners involved in this project that have their name known in music technology industry. And the main objective of this project is to develop or improve music information processing algorithms in terms of their scalability, robustness, and their generalizability, so that we can integrate this research software with industrial applications. I'm doing my research in the research lab called Center for Digital Music here in London. It's a world-leading multidisciplinary research group in the field of music and audio technology. And it's one of the largest research groups in its field globally. The span of the research topics within our lab extends from music information retrieval, semantic audio, web audio, digital signal processing, audio engineering, instrument design and sound design, music perception and cognition. So it's a very wide range of research topics that people are working on here. And our industrial collaborator from Sweden, Doremir, it's a company that develops applications for music users, songwriting applications that they have, music or singing voice training applications, and business-to-business solutions. One of the most interesting applications that they have developed, and I'm also in the process of adding extra features on it, it's called Scorecloud, which is available on Apple Store, which is basically like Google Translator, but for music. Basically, you sing through your phone, and then, as you see on the right-hand side, it transcribes the musical content into music notation. So I think it's a very handy device for musicians from all sorts of levels. So after some nice introduction, let me give a little bit of outline of what I'm going to talk about in the last half an hour or so. In the first part, I'll be talking about the basics of automatic speech recognition technology and one of the state-of-the-art methods in this field. In the second part, I'm going to talk about its application in singing voice. And this process is generally referred as automatic lyrics transcription in the literature. I'll be talking about the essential steps when we're processing song lyrics and how we construct our lyrics transcriber. Before I conclude my talk, I'll be giving a little bit of a demo of the lyrics transcriber that we built to give an idea about its potential applications and what it actually does. So this is the overall pipeline of information processing in that handy device, voice assistant, that you've seen in the first slide. So in this scheme, imagine we have this cute little Pac-Man guy on the top left-hand side, and then he speaks something to its phone, asks some questions or talk about its life whatsoever. And then the microphone in its phone converts this acoustic speech signal into an analog electric signal. Then, so there's this sound card, this microchip, embedded in your mobile devices that looks something like this, that converts this analog electric signal into a digital signal. It discretizes it, or it converts the signal into numbers, which essentially looks like something like this on the bottom left hand side of the slide. And once we have this digital signal, we can start our speech recognition process. First step is to extract some speech-related features from this digital signal. In the past, people have been extracting carefully engineered acoustic features to make sense out of speech. But in today's practice, the most common way is to use spectrograms or their scaled version, also called as mass spectrograms, or MFCCs, when we take the discrete cosine transform of the mass spectrogram. Note that there are also some work that use the original time domain signal for speech recognition. And then once we have the acoustic feature representation of the speech signal, then we have a speech recognizer, this brainiac-looking image here. And then it tries to make sense out of these acoustic features. And then it translates these acoustic observations into a human-readable format in a form of orthographic transcription, as you see on the right-hand side. So that is the goal. Translate human speech into text. That's what speech recognizers do. Traditionally, speech recognizers consist of three major computational blocks: the acoustic, the pronunciation, and the language models. And I'll be talking about the details of how we can build those in the next few minutes. So let's go back. Maybe I can show a signal. Well, maybe I'll skip the demo actually here. Well, what you see here is an utterance, is someone speaking the words that you're seeing in this spectral image. No time for losers, because we are the champions. These are the sequence of words that we are trying to predict given this acoustic image, this spectral image. And essentially, this is a sequential pattern recognition, considering that every word has a pattern, and then we are trying to build a system that is able to learn these patterns and then tries to make sense out of it semantically. So we achieve this with machine learning models. For those who don't have any idea about what machine learning is, I'll try to explain what it is in 30 seconds. It's going to be very broad, but I hope you get a sense what machine learning is. So what you see, the equation is actually, I think, is able to define what machine learning is in very broad terms. Y here, the Y symbol here, are the labels or the categories that we are trying to predict. This is the information about the real world that humans make sense out of. The letter X is the observations, the type of features that these categories, these real world information have. And what machine is trying to do is to learn a mapping, to learn a function, noted by letter F here. The machine is trying to learn a function that maps these observations between the real world data. And in our case, the speech recognizer is the machine, is the letter F. And we are trying to construct this F here, a mapping between acoustic observations and real world text. So let's move on to, let's do a bit more math here. The equation you see in the bottom is generally referred as the fundamental equation of speech recognition. And it defines our goal mathematically. Let me explain the terms here first. The letter W represents the word sequence. The letter X represents the acoustic features that we extract from the speech signal. And the symbol W hat is the word predictions that we obtain. So what this equation tells us is that is our objective, which is finding the likeliest word sequence given some sort of acoustic observation. So again, back to machine learning. As I said, our speech recognizer tries to learn that function between features and words. Generally, we apply a bias rule here. So we decompose the previous term here into the two terms here that you see in this equation. The equation on the left-hand side is referred as the acoustic model, which gives the probability of observing such an acoustic scene, knowing that it belongs to a certain word sequence. And the term on the right, PW, it gives the probability of observing a word sequence. And statistically speaking, this gives us a language model, which is intuitively encodes a grammar information. But solving this equation is difficult due to a few reasons. First of all, there are more than tens of thousands of words in the vocabulary of a natural language, which results in tens of thousands of classes that we will try to predict. And it becomes an intractable problem if you try to solve this equation directly. Moreover, even if we attempt to do that, it is not practical to include every word equally representative in a training corpus for a machine learning system. For this reason, words are decomposed into what is called phonemes. A phoneme is the basic sonic unit of speech. And according to the science of phonetics, words in a natural language can be represented by a sequence of a finite set of phonemes. And this set of these phonemes are, the phoneme types are determined with respect to their distinctive acoustic patterns. There are several ways of categorizing phonemes, but broadly speaking, we can talk about sonorous and non-sonorous events. We can exemplify non-sonorous events with voiceless consonants, sounds like P, T, K, sounds like this, that doesn't have distinctive sonorous events. And sonorous events can be exemplified by voice consonants, such as sounds like L, W, M, N, sounds like this. And obviously, all of the vowels are sonorous events. So based on these smaller sonic units, we can represent words using them. So an example of representing words into phonemes is given in this slide. Below, you see a sentence, "We are the champions," and below that, there is this phonetic representation. It's also called how the words should be pronounced. Then our task becomes phoneme recognition instead of word recognition. And our goal is to recognize the patterns of phonemes and learn the patterns of phonemes. But the phoneme patterns are not that straightforward to learn because of two major reasons. First of all, in human perception system, recognizing phonemes is a continuous process. So we recognize phonemes in a sequence manner. We don't recognize phonemes as standalone acoustic events. Moreover, phoneme patterns are generally affected by their surrounding sounds or by their surrounding phonemes. For this reason, a more accurate way to learn phoneme patterns is to use the structure, what is called the triphones, which is the concatenation of neighboring phonemes with a base phoneme. So in this slide, on the second row, in the image below, this is the phonemic representation of a word in terms of base phones or monophones. And we obtain triphones when we concatenate the neighboring phonemes for each monophone. So the equation that we see here in this slide summarizes up what we have just talked about. It is the fundamental equation of automatic speech recognition extended in terms of phonemes. And on top of the W and Q and W and X in this equation, note that Q represents the phoneme sequence, which you'll be seeing a lot in the following slides. So here is the mapping of the major computation blocks between the fundamental equation of speech recognition and the blocks that you see in the slide. So the acoustic model is generally associated with the term in the middle you see here. As I said, it gives us the probability of observing an acoustic scene, knowing that it belongs to a certain phoneme sequence. And the mapping between phoneme sequences and words are achieved by a pronunciation dictionary, which is usually curated by phonetic experts. And it looks like something like this. We have words and we have their phonetic representations. Once we have probabilities on the word level, we try to make sense out of these word sequence semantically using a language model. And hopefully, in the word prediction output that we will have something that is grammatically more relevant. Once we have all these probabilities, we obtain a graph, a complicated graph that looks like the image that you see on the right-hand side. This is called a lattice structure. A lattice is a cyclic, directed, weighted, labeled graph. And it is directed from left to right. In each branch in this lattice, there is a word prediction assigned with a probability. And this probability is represented as probabilities associated with each word in the sequence. Then our recognition procedure applies decoding over this graph with the objective of finding the likeliest path in this graph. And this is achieved efficiently using what is called Viterbi decoding. I'm not going to give the details of this procedure further due to time constraints, but if you'd like to learn more information about this topic, please refer to the concept of weighted finite state transducers. All right. So again, our task is to predict phoneme sequences, and our task is a sequential pattern recognition problem. And one of the most popular approaches to process sequential data is hidden Markov models. And hidden Markov models, the transition and emission probabilities are the two factors that characterize the model. In speech recognition, each phoneme is modeled with hidden Markov model. And in speech recognition, the emission probabilities or the output distribution is it corresponds to the phoneme posterior probabilities. This is the term here, and it gives us the acoustic model. In the past, in the history of speech recognition, there are many researchers have used many classifiers, like Gaussian mixture models, support vector machines. However, with the advent of deep neural networks, DNNs have become the standard approach of constructing an acoustic model. So I'm going to talk a little bit about how we train deep neural networks. In deep neural networks, if you use them for classification, we typically have what is called a softmax layer in the output, in the final layer, which gives us a probable distribution of the classes that we are trying to predict. And in speech recognition, the output of the softmax layer is considered to be the phoneme posterior probabilities. And this is the term that we'd like to obtain, and this is the term that we are optimizing our neural networks for. It is the gradient that we are constructing. So I'd like to talk a little bit about sequence discriminative training. This is a very scary-looking formula here, but it is the state-of-the-art approach in speech recognition. Generally, in deep neural networks, it is optimized with cross-entropy loss. But in sequence discriminative training, we use the loss function, what is called the maximum mutual information. And the objective of this function is to maximize the shared information between two sequences. And in the application of speech recognition, it is the ground truth word sequence that we have in our training data, and the hypothesis, the transcription produced by the speech recognizer. Hence, the optimization of the neural network is done on the sequence level. So it is a more efficient way of training because we have overall one loss compared to having frame level losses in the cross entropy training. Note that the objective of this function is to optimize the probability of observing an acoustic scene given its phoneme sequence and minimizing the gradient in the denominator in this equation, which is the probability of observing such an acoustic sequence, but minimizing the probability of observing this acoustic scene, which would correspond to other phoneme sequences in our training data. So our goal is to discriminate this acoustic scene with its given phoneme sequence. So there was a lot of information overload, I assume. If you have any questions upon this point, I'm happy to answer, and we can give a little bit of break, and then we will continue with lyrics transcription. Do we have any?
We didn't receive any question up to now.
All right.
And you were talking about the basics. So I would suggest that we continue the presentation and get the questions at the end.
Sure. I'm going to talk about more interesting stuff now. But that was just...
Well, it was also interesting, but it was the basic theory.
Yeah.
So if we get closer.
I'm just trying to share. All right. Well, let's keep on. Well, all right. So in this part, I'm going to talk about the application of speech recognition in singing voice. So I'm sure most of you are familiar with the automatic captioning tool of YouTube. In fact, it may even be automatic captioning me at this point. It's a very handy tool, and I think it's very impactful for many people in their work and also for everyday users. But have you recognized its performance on music, on singing voice? It is not as good as it is in spontaneous speech. And it's mostly because it's not optimized for singing, for music. Here's an example of what YouTube recognizes and what the original lyrics are. As you see, it is far from reaching to a robustness level that would satisfy an everyday user. So that's my PhD research problem. How can we transcribe the words in singing voice signals better than this and better than what is available in research, and to a performance level where we can use in industry, and essentially to bridge the gap between speech recognition and lyrics transcription. And my approach has been a straightforward one. I've been trying to adapt the state-of-the-art in speech recognition to singing voice. The first adaptation approach that I did is regarding the language model, is the grammar that I'm constructing for singing voice. So I've constructed a singing voice language model where I used a text corpus that consists of popular English language songs using the resources that you see in the slide. And most of these song lyrics we have retrieved it from online available free sources. But there are problems with the online resources. Usually they are not clean. They are usually uploaded by common users, and people don't pay attention. They don't upload these lyrics for the purpose of training a deep neural network, I suppose. So for this reason, we have to do some pre-processing steps when we're trying to train a language model. We have to apply some text normalization steps, such as numeric to alphabetic conversion, removal of non-alphanumeric characters, hyphenation, dehyphenation, or converting corrupted words into their canonical forms, etc. And once we have clean text, we can train an n-gram language model. Note that when we're training a language model, each data point is a line of lyrics. It's not a chorus of lyrics or whatever. It's a line of lyrics. And then we have constructed a singing adapted pronunciation dictionary because, as you may imagine, people tend to pronounce words in a different way when they're singing. And this is usually manifested with longer vowels or some of the omitted consonants or the interchange of vowels during the melody construction process. And there are no rules in it. And people usually articulate words depending on their artistic preferences. And it is really hard to model their pronunciations. But, well, to begin with, we have constructed a pronunciation dictionary modeling longer vowels, while we extended the representation of vowels in their pronunciation, as you see here. So gimme can be pronounced like gimme or gimme or etc. I'm not a very good singer, and sorry about that. And the other thing that we have to do is in lyrics, people come up with lots of different words, special words, and we need to generate their pronunciations. We need to generate pronunciations for these out of vocabulary words using a pre-trained grapheme to phoneme converter. What this grapheme to phoneme converter does is, given a word of letters, it generates its phonemic representation so that we can use it for our acoustic and language models. The acoustic model, like this is the most complicated part of this talk, so be prepared. Let me talk about the toolkit that I've used when constructing our acoustic model. I've used the Kaldi speech recognition toolkit. It's a state-of-the-art research toolkit, and that is commonly used by both for scientists and industry developers. And why we have used it? Well, it is scalable, it is robust, the code is easy to read, good documentation, and it's very open source. with Apache version 2 license. And it is developed by the community and commonly used by the industry. So it's a good device. I highly recommend of using it. When training our acoustic model, we have used singing voice data only, no speech data. And we have used these dataset, open source datasets, available only for research. It's called the DAMP dataset, Sing 300 times 30 times 2. You can obtain the data from this link. The data is collected by a karaoke application. And they're a cappella recordings, no musical background. And there are amateur singers from 30 different countries giving high amount of pronunciation variability. And the data set is gender-wise balanced. It is recorded by mobile devices, so it is representative of real-world data, I have to say. And the overall training data consists of 150 hours of audio recordings. So, step by step, how do we construct our acoustic model? I'm going to be a little bit technical at this point, for those who are interested in constructing a powerful lyrics transcriber. The first thing that we have to do is to obtain the phoneme timings. Phoneme timings are usually not available in training data because it's really hard to annotate them. For this reason, we apply bootstrapping via what's called a forced alignment. Using a pre-trained acoustic model, you don't need to learn about the details of this procedure, but know that this procedure provides us the timings of phonemes that we will be using for training our neural networks. It is crucial because the timings, we will train the neural networks based on the acoustic feature corresponding to the aligned timing information of these phonemes. As the acoustic features, we use a 40-band mass spectrogram. And so we know that every person has a unique spectral characteristic. To reduce this variability based on each singer, we apply what's called singer adaptive training. And we achieve this using singer identification feature embeddings, extracted what's called I-vectors. I-vectors is like a dimensionality reduction procedure where it tries to extract a global vector or a global representation of an acoustic scene. And we can use it to learn a global representation for each singer to be used for singer identity. So these are the features that we use. We input our deep neural networks. And we are using this lovely but scary equation as our training objective. As I said, we are optimizing sequences. We are not optimizing our neural networks on the frame level. So our artificial intelligence learns how to utter sequences in terms of uttering phonemes. I mean, this is an important aspect of this approach. I think that at least that's something that people that you should remember about sequence discriminative training. In the neural network architecture, the main block is it consists of time delay neural networks. Well, time delay neural networks are essentially one-dimensional convolutional neural networks, where the convolution is applied only on the time domain. So it is the objective of this operation is to learn context dependency over the time domain, just like RNNs. But I prefer to use time delay neural networks because they're faster to train, and according to my experiments, they learn better than RNNs, and they're parallelizable, so the learning is more efficient. But time delay neural networks, like we need to stack 17 of them to learn enough context dependency, longer context dependency. But the more we have time delay neural networks, the more complex the network becomes and harder to train. So because of this, I added, as a novel thing, I added 6 convolution layers in the front end before time delay networks. But we apply subsampling or pooling after convolution layers by means of dimensionality reduction. So in the beginning, we have future height of 40, but after the front end convolutional neural networks, we have a future height of 5. And that creates, that helps with the complexity reduction in the neural network. It's interesting because we increase the number of layers in the architecture, but the number of trainable parameters reduce. And some more details about training. We used 1.5 seconds chunks of audio, where we have 32 samples per mini batch. These are the details for neural network experts, by the way. And we train our neural network for 6 epochs. We start with a learning rate of 5 to the times 10 to the power of -4, and we apply learning rate decay, ending up at 10 to the power -5. To avoid overfitting, we apply regularization with L2 norm penalty and cross entropy loss. So this help neural networks to fine-tune too much on their training data. And to gain a little bit of performance improvement, we also apply data augmentation by means of speed perturbation. So each data point, we apply sort of time warping, making them shorter or longer. All right, this is how we train our artificial intelligence. I'm going to share my presentation, so if anything is not clear, you can go back to these slides. Evaluation. Usually, speech recognizers, speech recognition systems are evaluated in terms of word error rates, how well they can recognize words. And this is actually a ratio of the types of operations that we need to have to match the hypothesis, the transcription between a reference word sequence. There are other metrics depending on the granularity of the speech unit that you'd like to make. It can be done on phonemes, it can be done on characters, but this is the equation that we are evaluating our recognizers. Some of the results in our first publication, we were able to achieve 15% word error rate, and that's the state of the art in lyrics transcription in a cappella recordings. 15% word error rate is important result because there was a breakthrough in lyrics transcription research. Previously, researchers have been reporting results like 60, 70, 80%. And that's a big jump, and I think that's important. And also it's important because in its counterpart in speech recognition, IBM introduced their first commercial product, speech recognition commercial product, when the level of performance of their speech recognizer was at the level of 15%. So, these results are promising so that we can convert this research product into some sort of industrial application. And in the last MIREX, which is a public evaluation of music information retrieval algorithms, our algorithm resulted to be the best in a cappella recordings. We have better results, but they are still under review, so I cannot share it here. But I have to say, our results have improved 100% relatively. And this is the paper that's on the bottom that we made our publication. So I'd like to stop talking and show what this lyrics transcriber does. Hopefully, I can open Chrome. Right. I'm a poor Mac user at this point, so how do I go? Yeah. All right. All right. So I'm gonna show some videos on YouTube. I thought that was the safest way. All right. So let's see. So what you're seeing here, this video I recorded using the Sonic Visualizer software, which is an open source software for visualizing music signals, developed by Center for developed in Center for Digital Music. So let's go. The images that you're seeing here, by the way, this is the acoustic representation of the singing that you're going to be hearing, and this is the acoustic observations that we have trained our neural networks. So give them all a wait, I'm gonna start with, well, yeah, I'm gonna start with,
lower the volume down a little bit.
All right, I'm gonna put the volume down. Cool.
Thanks.
We are the champions, my friend, and we'll keep on fighting till the end. We are the champions, we are the champions, no time for lose. We are the champions, we are the champions, no time for losers, 'cause we are the champions.
All right, so another demo. So in this demo, first you will see you will hear the same utterance twice. In the first one, there's no lyrics shown, and I'd like you to recognize the lyrics by yourself and evaluate yourself how well you can do, and then we'll show what our lyrics transcriber does.
So give them all to me and I'll give mine.
Sorry, I'm gonna put down the volume a bit. All right.
So give them all to me and I'll give mine to you. Bask in the glory, all our problems, 'cause we got the kind of love it takes to solve them. Yeah, I got it. So give them all to me and I'll give mine to you. Bask in the glory, all our problems, 'cause we got the kind of love it takes to solve them. Yeah, I got it.
So yeah, I haven't done a proper Turing test yet, but my lyrics transcriber actually performs better than me. But I'm not a native speaker anyways. But anyways, so in this example, I'm going to show where, so in the previous examples, we had a clear linguistic content in English language. Here we don't. It's kind of like a vocal exercise. And that's kind of like the problematic case at this moment I'm tackling in. But I'd like to show what my lyrics transcriber recognizes in the case of non-linguistic content. Well, too much noise, sorry.
Bum bum. Bum bum. Bum bum.
Well, yeah, it can be but it can be other sounds. Well, yeah, I think that's interesting. This kind of output. So let's go back. Oh, that's an inception here. All right. So we did demo 1, demo 2, and demo 3. What's next? Well, there are still things to do for improving the performance of lyrics transcription. The data that I've been using, they have some inherent noise in them in terms of the lyrics timings and the text itself, etc. So that needs to be cleaned up. We can apply more data augmentation methods, spectral augment, and all sorts of things. We can generate weak labels to generate more data as well. Multilingual lyrics transcription is still not being tackled a lot in research. And also for lyrics transcription in polyphonic recordings, that's still a challenge. And I have some ideas on that, like genre-adapted training. And also we need to come up with a better pronunciation dictionary, that can handle the pronunciation variance in singing. Obviously, to do all of these things, we need more PhD and master students that are devoted for this task. There are many applications of this technology. Intuitively, we can apply it for karaoke applications, automatic subtitling, captioning tools, song alignment applications like in Spotify. It can be used for singing voice transcription. It can be used for songwriting tools as a sidekick technology. For cover song identification, not quite like Shazam, but imagine that you're singing a song and then you want which song is that, or like that you can't remember the name in a way. Well, Shazam can't do that. Google Humming can do that in a way. But yeah, you can use this technology for that. It can be used for educational applications, specifically for singing voice training. And it can also be leveraged for therapeutic applications, especially for dyslexia patients. And this technology, extracting lyrics from singing, has also its application for many tasks within music information retrieval research, like audio segmentation, metadata generation. And once we have the lyrics and their timings, we can apply music structure analysis, music emotion recognition, etc. So what's the take-home message from this talk? Well, I hope I was able to explain some of the basics of speech recognition and the state-of-the-art method in that, and also its adaptation to singing voice, and also what's called lyrics transcription. I talked a little bit about the data resources for constructing a lyrics transcriber and the essential preprocessing steps. And also, just now I have talked about the potential applications of this technology. Well, all my code are available in my GitHub account with open source non-commercial license. And for my other projects, please go and visit my website. With Barış, my previous supervisor in my master's thesis, we have also done Automatic Makam Recognition from Turkish music. And that is still the state of the art, I think. And there's the code for that. And if you have any questions, please go ahead and drop me an email whenever you'd like. So thanks for everyone's attention and being here with me on YouTube.
Thanks a lot for this nice presentation, Emir. And congratulations for the good results you obtained. Very happy to see that, well, it's really working. There are a few questions. The first question, okay, let me read the question. You may also read it directly. So in demo 1, transitions between some of the segments could be heard or detected. What's the reason for those? How could they be resolved? Well, that problems in transitions could be due to the streaming. Maybe there were no problems, but while we were watching YouTube, there were moments of disruption. Maybe That was the main problem, or
Um,
can you make sense? Well, maybe
I-
something I missed.
I'm afraid I have to agree with you because I have not put like a sonic indicators for each of the segments. So I'm not sure if it's the streaming thing or
Okay,
yeah.
then let's skip to the next one. Move to the next one. So Devrim asks a question: where do you think this field will move towards in the short or long term, in terms of techniques and algorithms and applications?
Well, yeah, I kind of talked about it in a way. So like, let me share my slide again. Well, in the previous one. So where does it go? As I said, I think so speech recognition research is an established field of research, and they have lots of training data that was curated very clearly and hand annotated, and they're like by the community. The labels and annotations are cleared and fixed. Since lyrics transcription is rather a new research field and it is not that established, I do think that some of the training data could be cleaned up a little bit further, for the reasons like timings of annotations, etc. So that's a major thing, I think. And other things, I think there's still some work to be done regarding polyphonic transcription. And I also think that we need to make a Turing test. We need to make a listening test, comparing the performance of average human listeners or transcribers and the machine, so that we can identify how can we improve based on human errors and types of mistakes that machines do, but humans don't. So I think that having a listening test would give us a more intuition regarding the development of this technology. So I think those are the essential steps that needs to be taken, and also the applications. I think there are lots of applications. It's just the performance of lyrics transcribers need to be a little bit improved further. As I said, I don't want to replicate myself, but all these applications that you see in this slide. I mean,
we don't see this slide.
Oh, am I not sharing it?
No.
Oh, that's my bad. Well, I thought I was sharing. Stop cam? No. Okay, share.
Well, not too critical. You were talking about it anyway.
Yeah, cool. Well, yeah. Can you see it now?
Yes.
So yeah, like these are the things that needs to be done: data cleanup, and also the Turing test. I think that's essential. And like these are the type of applications that I've already talked about. For instance, I mean, it could be used for music editing. I think it's gonna save a lot of time for video editors, post-processing people that creates music videos. If you use it for lyrics alignment, it can be used for music catalog creation when you have millions of songs in your data set, in your database, and you want to create metadata associated with each of these songs. It's a time-consuming thing when humans do it, when you have millions of songs, but this can automatize the procedure. So I think there are potential applications for this.
I have one short question. I guess you trained from scratch the models, right? You didn't apply transfer learning or taking a trained model, maybe from trained with speech recognition, data. Well, would that work, you think? I mean, would it make sense to try applying transfer learning, starting from a trained model, trained on speech?
That's interesting. Let me stop sharing my. Yeah, that's it. That was a thing that I'd like to try, but then I thought training from scratch works fine already. I think there's a potential there, but I would also take that approach with a grain of salt, because usually in transfer learning you have a powerful model that is trained on big data set, and then you just train it on you add few more layers, and then optimize the classification layer mostly that you added on top of your pre-trained model, and then you supposed to use a smaller data set, because the layers that you're optimizing are less in numbers, so you can't be optimizing them a lot with a huge data set. And usually transfer layers, they are not learning anything, but the new layers have a higher learning rate that they can learn faster. It can be done. I think it's a valuable, it's worth trying. But also in speech recognition, it is noted that training from scratch works equally well compared to transfer learning. So including data from different domains in your original training set works equally well in this sequence discriminative framework. So what I would say, a better approach to go for, which I haven't tried already, is to train a speech recognizer by means like a cross data set training, where you include speech data and singing data, and then you concatenate them, forming a single big training set. And that could work, may not work, but it's worth trying.
Thanks for the answer. So now it's about an hour, and we don't have more questions. So thank you very much for the presentation. I think it will be very useful, especially for those who want to start considering this task, researchers who will jump into this domain. It will serve as a really nice introduction. And well, it's also very useful that you share all your code, so they start from where you have left. That's a good opportunity for
I think it's
young generation.
Practice for 21st century scientists, reproducible and open science, because there's no other way to for other third parties to evaluate a scientific work. It's a time-consuming job to develop a software from scratch, and a lot of reviewers won't do it. And also so I encourage everyone to be open and be reproducible. And again, like I aim this talk to be like a lecture instead of usually long talks are more like conceptual talks. But since this research field is at its infancy, I'd like to draw more attention for brilliant and talented masters and PhD students that think this research field is interesting.
Thank you very much, Emir, and thanks to all who have joined, and who I assume, well, I think there will be many others to watch in the upcoming years. So it will stay here as a very useful resource.
Perfect. It's been a pleasure.
It's a pleasure to have you here.
Yeah.
Bye.
Bye.